The notes for Honors Precalculus Fall 2017 for Friday, November 21st. So we're looking at modeling power functions, and really power functions are just proportional relationships. And these are things that we've seen before. We've talked about proportions, and you've seen proportions many, many times. But now we're actually giving a name to them, that is, power functions. So the most generic form of a power function is a times x to the b power. Now, a is a number out by itself, and it's often called the constant of proportionality. And b is just the power on x. Now, the thing to note about b is that b is a real number. It's not an integer. A lot of people, based on their experiences, they've only seen a value of b that is an integer, but b could be a non-integer. Could be a decimal, could be a fraction. Now, for some quick examples of power functions you've seen before, how about this? Circumference equals 2 pi r. That's a power function. You're relating the circumference to the radius, and that right there is your constant of proportionality. Another one, if we're staying in the circle realm, would be this, pi r squared, where pi is your constant and r is being raised to the second power. And then finally, we could also go into 3 dimensions, 4/3 pi r cubed. And that is 4/3 pi is your constant. And so here we're relating the volume of a sphere with the radius. But all power functions follow this basic structure. So here for this example, we want to relate the period of time, that is how long it takes for a pendulum to swing back and forth, with its length. So that means time is going to be on one side of the equation, and length is going to be on the other side. Now when we say that it varies, that means that it's proportional to. No, that's different than equal to, because that means it's proportional to, so we're multiplying by some unknown constant. That is the constant of proportionality. And it says as the square root of its length. Now, as a power function, we can write that as L to the 1/2, because we've identified before that the square root is the same as the 1/2 exponent. So that's what this power function would look like. Now the next one is a little different, because here we're relating a planet's year to its distance from the sun. So y is going to be on one side and d is going to be on the other side. And it says it's proportional to, so one side has to have a constant. Now it doesn't really matter what letter you use. Some books tend to prefer k or n or a. It doesn't really matter. But what's different about this one is that it says the square of the year. So that means y is squared, but it also says the cube of the distance. So in this case, we have both sides having a power. Now some people are uncomfortable with that, and they say, well, we have to have one by itself. Well, you can still handle that by taking the square root of both sides. And so you can write it as square root of d cubed, or you can write it as d to the 3/2. You can write it like that. So for this one, we have the volume of a gas, and we're relating it to its pressure. So volume on one side, pressure on the other side. And because it's proportional, we put K, but it says inversely proportional. Now anytime you see inversely proportional, that means the exponent is negative, but they don't give us anything else. So that means the exponent is -1. Now this comes to us from a chemistry context, and you probably didn't see it written like this. Odds are you saw it written like this. K divided by P. And mathematically, these two concepts are the same. They're written the same way. So here we're given that a 1 liter gas exerts 3.2 atmospheres of pressure. So we put 1 in for volume, and we put 3.2 in for pressure. And so to solve for K, we get 3.2 equals K. Now that constant allows us to then use that throughout the rest of the problem. So then we ask, how much pressure will it exert at 0.8 liters? So we plug 0.8 in for volume, equals 3.2 over L. So we multiply L to the other side, so 0.8 L equals 3.2. And so L equals 3.2 over 0.8. So that means L equals, whoops, I don't know why I used L. It should be P. So P equals 4 atmospheres. That's what our pressure should be. Okay. Now the next one, we're talking about a piece of wood. And what we're relating is we are relating the breaking weight with its thickness. And it says it's proportional to the square of its thickness. So W equals K times T squared. Now we want to find the constant. Now in order to find the constant, we need this piece of information. It says a 2x4 inch piece of wood will break under a 200-pound load. So 200 goes in for W. Now when we talk about our thickness, what we're looking for is this length from here to here. So we say that this is 4 and that this is 2 inches. So we want the thickness from here to here. Now remember, this is a right triangle, so we're going to use Pythagorean theorem, and we get a length of square root of 20. So square root of 20 squared means that we get 20K on this side, so that means K equals 10. So now what we want is we want to find the breaking weight of a 2x6 inch board. So we have 10 in for K times, and we need our thickness squared. Now we're not talking about a 2x4, we're talking about a 2x6. So one that's 2 inches one way, 6 inches another way, and we need this diagonal length. And that turns out to be square root of 40. So we plug in square root of 40, and so we get 10 times 40, and so our breaking weight of this board is 400 pounds. So just by adding those 2 extra inches, we doubled the strength of it. We doubled its breaking weight. So once you find that constant, then you can use that for every subsequent problem, plugging in what you know. In this case, we knew the thickness. Now this one, now we're talking about the breaking weight of a piece of wood, and we're relating it to its length, and we say that it's inversely proportional. So that means it's going to be written as K times L to the -1, or W equals K divided by L. So to find K, we plug in the length, which is 8, and the breaking weight, which is 40. So 40 in for W, and 8 in for L. And so when we multiply the 8 over, we get 320. So that is our constant. So now we want to find the length of a board that will break under a 75-pound load. So we plug 75 in for weight, and 320 over L. So we multiply the L over, and we divide by 75. And so then we divide 320 divided by 75, and that gives us 4.26 feet. And so that is the length of a board that will hold 75 pounds. Now what's unique about power functions, unlike others, is that you can combine multiple inputs. And so here we're not only relating weight to length, but thickness as well. So here what we're basically doing is we're just going to mash those two equations together that we found. So we have T squared on top and L on the bottom. So to find the constant, now we have to plug in the weight, which is 150, the thickness, which was square root of 20 that we used, and the length is 8. So we're going to multiply 150 by 8, and so we get 1200 equals 20K, and then divide by 20, and we get 60. So that is our constant. So now we want to find the breaking weight of a 2 by 24 piece of wood that is 16 feet long. So our constant is 60, our thickness, which we'll find in a second, and then our length is 16. So now we're talking about a piece of wood that is 2 inches one way and 24 inches the other way. So we need to find the thickness of the diagonal. So using Pythagorean theorem, we get the square root of 580 is our thickness of this diagonal. Now fortunately, when we square that, that will just become 580. So 60 times 580 over 16. And then that gives us 2,175 pounds. So that is our breaking weight. Now, the phrase that is used when we have multiple inputs is often called jointly proportional, but we'll be going over that on Monday when we return. Now, the last idea is what we were dealing with on our warm-ups from Monday and Tuesday. And the warm-ups were basically problem 64 from section 2.2. And the idea is that we've seen x squared enough that we know what its shape is. It looks like that. And we know what x cubed looks like. We've seen that enough. Shaped like that. Now x cubed is an odd function, x squared is an even function. But with a power function, we bring in the idea of what about decimals? What's going on here? Well, instead of decimals, it's much better to think of them as fractions, because that's what problem 64 was all about. It was asking how would the function behave under different exponents? And so we have 12 over 5. So we have an even number on top and an odd number on the bottom. So that means this is going to be an even function. And so if you check Google Classroom for the warm-ups from the past 2 days, you'll see what we worked on to get to that. And so this is going to look very much like x squared. Not identical to, but it's going to be very much like it. Now looking at x to the 2.5, that's going to be x to the 5 halves. And so we have an odd number on top and an even number on the bottom. And so that means that this is going to be neither. So this is going to look like half of an x squared graph. It's only going to go up like that, and it's not going to exist over here. Down below, x to the 2.6. Now 2.6 as a fraction is going to be 13 over 5. So both our numerator and our denominator are odd. And so that makes this an odd function. So this graph is going to look very much like x cubed, but be different from that. So if you need to review that, go back to Google Classroom and look at the warm-up links that I posted there for November 20th and November 21st to see what we were talking about. If you have any questions over the rest of these notes, please email me and I will get back to you right away. Thank you.